Alright, welcome to unit number 3. We're doing video number 1, which is right on the screen right here for you. We're doing sound this chapter, so I'm kind of excited about it. This is kind of a fun one to talk about. Now, we've already talked about sound a little bit already, so I'm going to start you off with a quick review, and then we'll start diving into some of the new stuff. So, now I can't find a pencil that works. I know you're laughing at me. Here we go. Alright, so review of sound. Let me just zoom in here just a smidgen. Pull this out. Alright, here we go. Review of sound. Sound, if you remember this, is classified as a longitudinal wave. Now, what does that mean? Well, remember that if I go to my diagram here real quick, I'm going to kind of skip down. This is a transverse wave. Remember this? So the wave will move this way, but the medium itself moves up and down, and this is going to be at a 90-degree angle. That's transverse. That's not what sound is. Sound is a transverse wave. So the wave, the wave is going to move this way, and then the medium is going to move this way. So transverse, the wave goes this way, the medium moves up and down. Longitudinal, the wave moves one way, and then the medium moves in the same direction. Those two are parallel. So, for example, in a sound wave, what you're going to have is an area of high pressure, and then an area of low pressure, and then an area of high pressure, and an area of low pressure, and an area of high pressure, and back and forth and back and forth and back and forth and back and forth. And so the waves themselves actually move left and right. I'm sorry, the molecules themselves actually move left and right if you were to actually watch them, and the wave then will move left and right as well. We call this area right here a compression. Alright, so that's a compression. And then we call this area right here a rarefaction. Compression is where you have high pressure. And a rarefaction is where you have low pressure. Okay, so everything's kind of, let me move it so you can see it. So compression is where everything's kind of bunched together. That's why it's high pressure. And low pressure is where the molecules are spread apart. That's why you get low pressure. So if we go back up to the definition here, or just the first little bullet point here, sound is classified as a longitudinal wave or pressure wave. Actually, we could probably add a third in here. We could add actually a compression wave as well. Alright, and all this means is that the wave moves parallel to the medium, and that's what we were trying to illustrate right here. So the wave moves back and forth. The wave will move this way, and then the material or the medium will move back and forth. So those two are parallel to one another. Alright, moving along. Sound, just review, we've talked about this already. Sound travels faster in solids than in gases. Alright, and we've talked about that before. So actually sound does not travel as fast in a gas as it does in a solid. So if you if you take two rocks and you're underneath the water and you clap them together, that sound in the water will travel much quicker than it does in air. And the reason for that is because solids and liquids tend to be more elastic. Now, what does it mean to be elastic? It means that the molecules, if you stretch them out, will come back to their normal place. For example, steel. If you bend steel, steel will bounce back a little bit. It's elastic. Putty is not elastic. If you change the shape of putty, it won't bounce back. If you hit putty, it's not going to bounce back. So that's why it's not elastic in this sense. Okay, the next one we've talked about. Sound travels faster in warm air. Alright, and we've talked about that before. Alright, moving along. Sound propagates or moves through air when one molecule collides into another air molecule. So this guy hits this guy, and this guy hits this guy, and this guy hits this guy, and just keeps pushing that compression through the air. And then that air molecule, back down to here, that air molecule collides into the next air molecule, and so forth. So it's almost like the domino effect. So, and that's what I've got next here. So sound moves through air similar to a wave moving along a row of dominoes. Okay, so one domino hits the next, which hits the next, which hits the next. That's the way air travels through the air. So one domino or air molecule hits the next one, and then the wave continues to move through the dominoes or through the air. Alright, now, switching topics ever so slightly, I have a tuning fork right here, and I'm just going to kind of take this out. And so, real simple tuning fork. A couple things with tuning forks. You're going to be using tuning forks a little later in this unit. We never want to take a tuning fork and hit it against a hard surface. The reason for that, tuning forks then will get little nicks and dings in them, and those nicks and dings actually change the properties and the frequencies of the tuning forks, and we don't want to do that. And this, matter of fact, I have a number of tuning forks that you're going to be using that are brand new. You all will be the first ones to use those tuning forks, which is kind of cool. And notice this one has no dings in it at all. It is nice, clean, wonderful tuning fork, and when you're done with it, it will be nice, clean, and with no dings or no marks on it. Alright, so basically, if you want to strike it to make it ring, the best thing to do is to get a mallet. Okay, and I've got a mallet right here. I don't have a lot of mallets for us to use, so plan B is I've got PVC pipes, like plastic pipes, and those tend to work well. So you just strike the tuning fork around that pipe, and you can make it ring that way. So the question is how does a tuning fork make sound? Okay, you can hear it right there. I'm holding it up next to the microphone. I know you can't see it on the video there. Okay, how does it make sound? Well, here's how it works, and I have a demonstration. I'm not sure how well this is going to work on video, but we'll give it a whirl anyway. I have a beaker of water here, and you can try this when the video is done. Just go grab a tuning fork from the black cart and a beaker of water, and I'll have some beakers out. You can fill it up with water and give this a whirl. If you take this guy and put him in here, let me try it one more time. So, do you see that? Okay, it literally splashed the water all over the place. Let me try it again. I just dried it off. So let me strike the tuning fork again. Okay, it's vibrating. I'm not sure if you can hear the sound. And then if I put it in, ooh, I waited too long. I waited too long. That's not good. Let me try it one more time. So striking it, and it should have splashed a little bit, and I'm not getting much of a splash. There it is. There's a little bit of a splash. It's kind of cool because you can actually see it right along the edge, right here, where it actually splashed. And so all that's evidence, the simple fact here, is the evidence that when you strike a tuning fork, the tines of the fork literally move back and forth. And when a tine moves one way, two things are produced. So when a tine moves this way, on this side, on the leading edge, it pushes all the air molecules together, and what's produced is a compression. And then on the back side over here, it stretches out the air molecules, and so you produce a rarefaction. So when it moves to the right, compression and rarefaction. When it moves to the left, a compression over here and a rarefaction over here. And so it just moves back and forth and back and forth and back and forth and back and forth. Compression followed by rarefaction, compression followed by rarefaction, and voila, you have sound. So, here we go. So back in your notes, let me zoom in just a smidgen here. So here they are. So tuning forks produce sound when the tines or prongs move back and forth. And I did my demonstration, so if you want to see a nice little diagram, here's Here's my best effort at a diagram. You know my diagrams. They're not very good. But there's my tuning fork. And when the time moves to the right, a compression's produced over here, and a rarefaction's on the other side. And then when it sweeps back the other direction, you have a compression and a rarefaction. And that's basically how it produces sound. And then your eardrum, which we talked about last unit, can detect that sound. All right. When a tine moves, on the leading side of the tine, a compression is produced, and on the back side of the tine, a rarefaction is produced. All right, next page. Getting close to the end of the first video. This one's a little longer than I anticipated. All right, pitch. Pitch is, you've heard of that term before. Some of you may know it. Pitch is how high or how low a sound is. Okay, so pardon my inadequate singing abilities, but a high pitch would be like this, and a low pitch would be like that. That's all it is. Okay, and when you think about pitches, high pitches correspond to high frequencies. So you could think of pitch and frequency in terms of sound kind of as the same thing. Now, humans don't hear all the frequencies that are produced. So a young person, now when we use the word young here, we're using the word young because a young person has really good hearing. And so a young person can, like yourself, a young person can normally hear pitches with frequencies from about 20 hertz, let me put the unit behind there, to about 20,000 hertz. So that's the range. So low down here, high up here. Okay, and those are your pitches. And anything between there, humans can hear. Normal humans. Now, what's interesting is, as we grow older, our hearing range shrinks. Okay, so instead of hearing 20, we might hear 40. And instead of hearing 20,000 hertz, we might only hear 10,000 hertz. And it's this side of the frequency, it's this side of the end of the range that is really harmed. So especially at the high end. Some of you know this because some of you set your cell phone ringers to really high pitch. And that high pitch, teachers, old like me, 41 years old, can't hear those high pitches. However, you can. And that'll signal to you that your cell phone went off. Okay. Also, some of you will know that the computer cart in the back of my room has a really high-pitched sound, and it drives you crazy. Unless I'm standing right next to the cart, I literally cannot hear it. And I know it drives you crazy, and that's why you asked me to unplug the cart, because you're going nuts. Now, what happens if we're below 20,000, and what happens if we're above, what happens if we're below 20 hertz, and what happens if we're above 20,000 hertz? Well, here's what goes on. We call those infrasonic and ultrasonic sounds. So infrasonic sounds are sound waves with frequencies below 20 hertz. Okay, now where do you experience these? You experience these in several different places. One, elephants. Okay, elephants communicate with very low sounds, and those low sounds can travel great distances. Whales can communicate with very low sounds. That doesn't mean they don't communicate with high sounds, but they can communicate with very low sounds. And also what's interesting is earthquakes produce very low sounds at frequencies that humans can't hear. Next one is going to be ultrasounds. Ultrasounds are going to be higher. So those are going to be above 20,000 hertz. So examples of ultrasonic waves include dog whistles and, girls, you'll know this, ultrasounds. So when you are pregnant, and you want to have a picture of your baby before it's born, doctors will do an ultrasound, and they're using frequencies that are higher than the frequencies at which you can hear, which is kind of cool. All right, and then humans cannot hear infrasonic and ultrasonic. All right, there it is, and enjoy the rest of the unit.